everyone, I'm Alireza from Queen Mary University of London. Today I'm going to present Backdraft, a lossless virtual switch that prevents the slow receiver problem. Packet loss is a problem. Packet loss impacts tail latency, packet loss degrades throughput, and packet loss wastes compute resources at the end hosts. Packet loss can occur in the network. We all know in-cast workloads that cause packet drop in the data center network. There are multiple papers recently that address similar problem. Now, packet loss can also occur at the end hosts, where we have a single machine that we have multiple applications deployed on this machine, and all of them are connected to the network via 100 gigabit per second network, for example. To explain why we have packet loss at the end hosts, I'm going to speak about vagaries of CPU performance. Here is our data center and our end host. We have a virtual switch deployed on our end host. We have a 100 gigabit per second NIC connected to the virtual switch. And this is our application. Here is a port that connects this application to the virtual switch. The question here is, what is the bandwidth of this particular port? It turns out that the performance of these CPUs allocated to this application. And unsurprisingly, CPUs are unpredictable. So if you're sending packets from a faster port to a slower port, then we're going to have queue buildups and eventually packet loss at some point. This is what we call slow receiver problem. Slow receivers are applications unable to keep up with the offered load. This is not the first time we are talking about slow receivers. This has been introduced in papers from industry and academia. Now, we present Backdraft, which is a lossless virtual switch that solves this slow receiver problem. Lossless virtual switching is actually challenging because if we do it naively, we end up with head-of-line blocking, congestion spreading, and wasted compute. Here is a high-level overview of Backdraft. Backdraft provides per-flow queuing in the virtual switches. It implements back pressure all the way to the applications, and it allows for higher throughput and lower tail latency. And with that, I'm going to move to the motivation behind the Backdraft. Insights of Backdraft. Slow receivers are pervasive. We conducted an experiment to understand how many cores memcache you require to achieve 100 gigabit per second. And it turns out that it requires 32 cores to be able to do this. Now, we repeated a similar experiment with NGINX, and NGINX requires 16 cores to achieve 100 gigabit per second. We also tested with a simple application like iPerf3, and the interesting bit about it is that this application doesn't have a complex logic, and all it does is networking functionality. And yet, it requires 6 cores to achieve 100 gigabit per second. We repeated similar experiment with DPDK-based implementation of, for example, memcached, and the results are similar. The message here is that the application design is actually important to derive line rate or higher rates. The second insight is that slow receivers manifest at microsecond scale latencies. We collected traces from the previous experiment to understand what happens at short time spans. It turns out that for memcached, we have 40 gigabit per second throughput variation over 100 microseconds. And we collected traces from NGINX experiment as well, and NGINX also shows a similar situation, where we have 40 gigabit per second throughput variation over 100 microseconds. And it's important to understand that 40 gigabit per second is actually beyond what a single core can handle regarding packet forwarding. Third insight, packet loss occurs in presence of Homa, a state-of-the-art congestion control protocol. We conducted an experiment to understand what would be happening if we have a server application based on Homa where it has less number of cores than it's supposed to. And in this particular case, where we have one single core, we'll see 10% drop ratio that impacts RPC completion time significantly. And as we increase number of cores available to the Homa server application, we'll see less and less packet loss ratio, and eventually better overall RPC completion time. Fourth insight, standard lossless techniques cannot be used in the virtual switching realm. Here we have rate limiting, we have back pressure, we have credit-based approaches, and picnic at Google system. Rate limiting is not suitable because we don't know what is the maximum line rate when we are running on a CPU. And back pressure is actually notorious regarding head-of-line blocking and congestion spreading. And credit-based approaches actually incur an extra RTT to converge to a particular rate. And picnic wastes CPU due to its design flaws. And with that, I'm going to go to Backdraft design to understand how we solve these problems. Three components of Backdraft. The first component is dynamic per flow queuing. The second one is Doorbell queues. And the third one is Backdraft overlay network. Dynamic per flow queuing avoids head-of-line blocking problem and has on-demand memory usage. Doorbell queues avoid wasted CPU. And Backdraft overlay network avoids packet loss and congestion spreading. The key idea behind the per flow queuing, though, is that if each flow has its own separate queue, then each flow can be paused and resumed individually without the head-of-line blocking problem. Before jumping into per flow queuing, let's understand why do we lose packets. Here we have multiple senders and 2 receivers, and if our senders send packets at a rate that the receiver cannot keep up with, then we're going to have packet drop at one of the receivers, for example. The question is how we can avoid this packet drop. The way to do this is to send pause frame to the upstream senders. But this is not going to end well because we end up with head-of-line blocking problem. As you can see, the red flow, which has nothing to do with the congestion, is actually blocked by the blue flow, where is a culprit for this congestion. Now, how to solve this problem? With per flow queuing, we can allocate or dedicate a separate queue for every single flow. With this, you can see that the red flow can easily go to its destination with that being impacted by the blue flow. And if we want to pause the blue flow, we can pause them because they are in a separate queue. Now, there's a trade-off in designing per flow queuing. Overall memory is limited at the end hosts. We can have a large number of short queues, for example, but the problem is it has low burst absorbance and it has high flow isolation though. High flow isolation comes from the fact that we have large number of queues, and low burst absorbance comes from the fact that we have short queues. On the other hand, we can have a small number of long queues where we have low flow isolation and we have high burst absorbance. This is exactly why we present dynamic per flow queuing to address this trade-off. Dynamic per flow queuing follows 2 basic principles. First, on-demand queue allocation. Second, on-demand queue resizing. Here is how dynamic per flow queuing works. Let's say we have a new flow, we allocate a new queue for it, and it starts building up, and then once we reach a particular threshold, then we resize this queue with an extended ring. We have a new flow in the system, so we allocate another queue, and it starts building up. Now, meanwhile, our receiver consumes some of the packets in one of the queues, and because we have empty ring, then we reclaim that extra and extended ring buffer. This is how dynamic per flow queuing works. Doorbell queues. Per flow queuing is not scalable and it wastes CPU cycles. We experimented with BESS, an existing virtual switch, to understand how we can extend and how we can push this virtual switch to support a large number of queues. And as you can see, BESS cannot sustain its throughput as we scale the number of queues to a large number. And this is exactly the key idea behind the Doorbell queues. Backdraft only busy pulls 1 queue per CPU core regardless of the number of created queues. This is how Doorbell queue would work. Here we have our data center, we have a NIC that it has RXQ and TXQ, and here's our application that we're going to focus on the receive side. And as you can see, we have a Doorbell queue added to the application interface. Let's say we receive a batch of packets, and because we got two flow, we created two queues, and we pushed two different Doorbell messages into the Doorbell queue. Now, these Doorbell messages are pointing into the relevant queue regarding their data. And all application does is pulling from the Doorbell queue and not the data queues. It reads from the Doorbell queue, it reads the Doorbell message then, and finds where the data is actually located. And with this information, it can directly go to the queue and pulls the packets. Again, it reads from the Doorbell queue, finds the Doorbell message, reads the Doorbell message, and finds the data actually relevant to that Doorbell message. Meanwhile, the DPFQ that we just talked about reclaims the empty queue here. So the next step would be reading the data packets, because we understood from the Doorbell message where they are actually. So this would be the key functionality of the Doorbell queue that saves a lot of CPU in the virtual switch. Now I'm going to go over Backdraft Overlay Network. I'm not going to go in depth because of time limitation. Please go look at the paper for more detail. Backdraft Overlay Network. The key idea behind this component is that we can utilize large buffering capacity at the end hosts. What do we do with this capacity? We can buffer more packets at the end host because we have more memory compared to what we got in the network. And then we can send pause frames or overlay pause messages to the upstream virtual switch. And the upstream virtual switch can later on decide what to do with this message. For example, it can stop reading from the application that is causing the congestion. Now, Backdraft Overlay Network can solve congestion spreading problem due to slow receivers, where even BFC, a state-of-the-art approach that is presented earlier in this conference, cannot solve. For more information about Backdraft Overlay Network, please look at the paper. I'm going to go over the Backdraft evaluation. Two main questions that we want to cover in this talk is that, can Backdraft solve problems with existing congestion control protocols that still aren't solved? Second, we want to know, how does Backdraft impact the real-world application performance? We experimented with Homa DPDK-based implementation, and we want to know how this application would perform with and without Backdraft. First, we run it with BESS, an existing approach, and then we run it with Backdraft. Here is the results. For RPC completion time, we can see Homa that can sustain higher throughput with lower latency with the small messages. Now, if you look at the large messages, we can also see the similar result. So Backdraft can improve performance of existing congestion protocols as well. Now we want to understand, how does Backdraft impact the application performance. Here is a real application like a key value store, memcached. We have mutilate to generate workload for this application, and we have a UDP app, which is a non-cooperative workload that creates a lot of packets towards its receiver. And the receiver of this UDP workload generator can be slow, and we'll see in a bit. So we have different types of workload at the same time, and we want to report the performance of memcached as our application. And it's worth mentioning that there is a vSwitch in the middle, and this is a single node experiment. Here is our results. We have three types of receivers: fast receiver, slow receiver, and slower receiver. The slow receiver spends 500 cycles doing nothing or being idle. The other slow receiver spends 5,000 cycles being idle or doing nothing per request, to imitate being a slow receiver. Now, our baseline is a lossy approach, and then we have back pressure, and then we have dynamic per flow queuing. Dynamic per flow queuing brings us a lot of latency improvement because every single flow will get its own separate queue. We have two more components, Doorbell queues, that the main benefit of Doorbell queue is going to be on the CPU or throughput that we'll see in a bit. Overlay network wouldn't be that impactful in this particular scenario because it's a single machine scenario. Overlay network is going to help us in cluster-wide scenarios. Again, we have a similar experiment, and we have similar applications, and we have similar baseline. We're reporting throughput here. First, we have lossy, and then we have back pressure. Back pressure is going to have less throughput because of on and off scenario that we will face. And the interesting point is that dynamic per flow queuing will have even less performance than back pressure and lossy, except for the fact that it has some improvement in a very slow receiver case. But why we have a slowdown with dynamic per flow queuing in general? The reason is that dynamic per flow queuing is actually imposing a lot of CPU overhead. And that's what's going to be solved by Doorbell queues. Doorbell queues are reviving the lost CPU cycles from the dynamic per flow queuing. And here is the result with overlay network, which is not going to be significant because it's the single node experiment. So the message here is all of the components of backdrafts are necessary and complementary in general. So here is the takeaways of backdraft. Slow receivers are pervasive. Dynamic per flow queuing or Doorbell queues and overlay network are all complementary and necessary. And backdraft can achieve up to 20x better tail latency compared to a lossy approach. Our code is open source, and with that, I'm happy to take questions.